Hi everyone, so today I'll be going through the data analysis section of the 2019 Further Maths Exam 2. So question number 1, table 1 shows the day number and minimum temperature in degrees Celsius for 15 consecutive days in May 2017. Which two variables in this data set is an ordinal variable? Which of the two variables in this data set is an ordinal variable? So it's referring to day number or minimum temperature. We know minimum temperature is a categorical, it's a numerical variable because we're recording, the degrees, temperature in degrees Celsius, and day number clearly shows an order. So 1, 2, 3. There's an order to the days recorded. So therefore, day number is the ordinal variable. 1b. The incomplete ordered stem plot below has been constructed using the data values for days 1 to 10. Complete the stem plot above by adding the data values for days 11 to 15. So if we go to this table over here, we know for day 11, the minimum temperature is 7.5. We know for day 15, the minimum temperature was 7.7. So basically we have to enter these values in the stem plot below. So we know day 11 is 7.5. The key over here gives us an indication that 7.5 would be like that. So we go down, 7 is over here, 7.5 therefore would be there. And day 15 is 7.7. So therefore on the stem plot, 7.7 would also be there. Question 1c. The ordered stem plot below shows the maximum temperature in degrees Celsius for the same 15 days. Use the stem plot to determine the value of the first quartile. So to find the value of the first quartile, we first need to find the value of the median. So the rule for the median is m equals n plus 1 on 2. So we know in the question it gives us n is 15. So we sub 15 into the formula, and we get 8. So count 8 from the start, from the lowest number. So 9.2 temperatures is our lowest number. So you start from here. So 1, 2, 3, 4, 5, 6, 7, 8. So the median is 13.7 degrees Celsius. Now basically you calculate the median of this section over here to find the first quartile. So there's 8 numbers there. 1, 2, 3, 4, 5, 6, 7. Sorry, there's 7 numbers there. So the median of that section would be 7 plus 1 on 2, which equals 4. So you count 4 from the start. 1, 2, 3, 4. So therefore 12.2 degrees Celsius is the first quartile. The value for the first quartile. CII. The percentage of days with a maximum temperature higher than 15.3 degrees Celsius. So if we look at the stem plot, the temperatures that are higher than 15.3 degrees Celsius is 15.5, 15.6, and 16 degrees Celsius. So therefore 3 days have a temperature higher than 15.3 degrees Celsius. So 3 on the total number of days, which is 15, times that by 100 to make it a percentage. And if you put that in your calculator, you get 20%. So therefore 20% is the percentage of days with a maximum temperature higher than 15.3 degrees Celsius. Question 2, the parallel box plots below show the maximum daily temperature and minimum daily temperature in degrees Celsius for 30 days in November 2017. Use the information in the box plots to complete the following sentences. For November 2017, the interquartile range for the minimum daily temperature was. So you look at the box plot for the minimum daily temperature, and into the rule for the interquartile range is interquartile range equals Q3 minus Q1. So we know that this point over here would be Q1. This would be the median. This would be Q3. So therefore the interquartile range would just be Q3 minus Q1. So Q3 is 17 and Q1 is 12. So Q3 minus Q1, which is 17 minus 12, which gives you 5. So therefore the interquartile range for the minimum daily temperature was 5 degrees Celsius. AII, the median value for maximum daily temperature was something degrees Celsius higher than the median value for the minimum daily temperature. So first step is to find the median value for the maximum and minimum daily temperature. So for The median for the minimum daily temperature is 15 degrees Celsius, and the median for the maximum daily temperature is 25 degrees Celsius. So if we do 25 minus 15, that gives us 10. So that basically indicates that the median value for the maximum daily temperature was 10 degrees Celsius higher than the median value for the minimum daily temperature. AIII, the number of days on which the maximum daily temperature was less than the median value for the minimum daily temperature was. So we look at the median value for the minimum daily temperature, that's 15. So 15 is over here. So we're trying to find the number of days in which the maximum daily temperature was less than the median value for the minimum daily temperature. So we only have one outlier, which is less than the median value for the minimum daily temperature. So therefore, it was just 1 day. To B, the temperature difference between the minimum daily temperature and the maximum daily temperature in November 2017 at this location is approximately normally distributed with a mean of 9.4 degrees Celsius and a standard deviation of 3.2 degrees Celsius. Determine the number of days in November 2017 for which this temperature difference is expected to be greater than 9.4 degrees Celsius. So we know the mean is 9.4 degrees Celsius. I've also drawn the normal distribution below, which you need for this question. So we know that the mean is 9.4 degrees Celsius. And we want to determine the number of days in November 2017 for which the temperature is greater than 9.4 degrees Celsius. So if you add all the percentages on this side, it's actually 50%. So we know 50% of the days in November 2017 are going to be greater than 9.4 degrees Celsius. So 50% is 50 on 100. And we need to know how many days there are in November. In the question, it says there are for 30 days in November. So we do 50% times 30. And if you put that in your calculator, you'll get 15 days. So therefore, the number of days in November which have a temperature greater than 9.4 degrees Celsius is 15 days. Question 3, the 5-number summary for the distribution of minimum daily temperature for the months of February, May, and July in 2017 is shown in Table 2. The associated box plots are shown below the table. So Table 2, it shows the 5-number summary for February, May, and July. And the parallel box plots are also given. Explain why the information given above supports the contention that minimum daily temperature is associated with month. Refer to values of an appropriate statistics in your response. So usually I like to refer to the median, and we're trying to determine if there is an association between minimum daily temperature and month. Usually when it says associated, there's usually a difference. So if we're comparing the median, for example, we're trying to look for a difference in the median. So if we go back to the table, we look at the median values for each month. February has a median of 10.9, May has a median of 7.5, and July has a median of 5. So basically there's quite a difference between the median for each month. So therefore there would be an association. And even if we look at the parallel box plots, 10.9, 7.5, and 5, there's a clear difference between the values of the median. So to start off the statement, I'd say yes, there is an association between minimum daily temperature and month, and after this I'd give a reasoning for this statement. So I'd say this is because, and I'd refer to median. So I'd say this is because the median minimum daily temperature for February is so we know the median for February is 10.9, which is greater than. So you have to have a statement which is greater than, and you refer to May. So which is greater than the median minimum daily temperature for May. We know that the median minimum daily temperature for May was 7.5 degrees Celsius, and you also say which is greater than, and refer to July next, which is greater than the mean, which is greater than the median. So the median daily temperature for July, and you would insert the median value for July, which was 5 degrees Celsius, and therefore that would be your response. Question 4. The relative humidity percentage at 9 a.m. and 3 p.m. on 14 days in November 2017 is shown in Table 3 below. A least squares line is to be fitted to the data with the aim of predicting the relative humidity at 3 p.m. from the relative humidity at 9 a.m. Name the explanatory variable. So in the question here it says a least squares line is to be fitted with the aim of predicting the relative humidity at 3 p.m. So if you're predicting something, that's going to be a y variable, which is your response variable, from the relative humidity at 9 a.m., which is x. So from the relative humidity at 9 a.m., x, which is your explanatory variable. And therefore, the explanatory variable is humidity at 9 a.m. Humidity 9 a.m. 4b, determine the values of the intercept and the slope of the least squares line. Round both values to 3 significant figures and write them in the appropriate boxes provided. So first step, open up a spreadsheet on your calculator and then enter the values of relative humidity as your explanatory and your relative humidity at 3 p.m. as your response variable. So just enter 9, just call that N. Let's just call humidity at 9 a.m. N and humidity at 3 p.m. We'll call that just T. So enter the values for 9 a.m. 100, 99, 95, 94. Then enter the values for relative humidity at 3 p.m. Then once you've done that, go into one of the boxes right next to opposite, just go into any of the boxes in the second row, hit menu 4, statistics 1, and then hit 4 for linear regression. And then we want our x variable to be humidity at 9 a.m. So you look for that variable. Sorry. And then in the Y you enter humidity at 3 p.m. So look for T, which is what we entered here. T, and then hit enter. And then you get your values for A and B. So on your calculator, we got A is negative 1.2 6 to 3 significant figures, and B is 0.765 to 3 significant figures. Question 4C, determine the value of the correlation coefficient for this dataset. Round your answer to 3 decimal places. So for this question, all you need to do is just look at your calculator. The correlation coefficient is the value for R. So if you look at your calculator, the value for R is 0.871. And the question wants us to round it to 3 decimal places. So 0.871 is the value of the correlation coefficient. Question 5. The scatter plot below shows atmospheric pressure in hectopascals at 3 p.m. plotted against the atmospheric pressure in hectopascals at 9 a.m. for 23 days in November 2017 at a particular weather station. A least squares line has been fitted to the scatter plot as shown. The equation of this line is as the following, and then 5a, interpret the slope of the least squares line in terms of the atmospheric pressure at this weather station at 9 a.m. and at 3 p.m. So basically you should have some sort of structure for interpreting the slope in your notes. So what I would have in my notes is for every increase in the value of x by 1, and then you'd insert the units over here, the y value will increase by whatever the slope is. So in this case, for every increase in the x value, we know that the x over here is the pressure at 9 a.m. So you place the x value with, for every increase in the pressure at 9 a.m., for every increase in pressure 9 a.m. by 1, what pressure at 9 a.m. is in hectopascals. So write by 1 hectopascals. The y value, we know the y value is pressure at 3 p.m. So you replace that with pressure at 3 p.m. So for every increase in the pressure at 9 a.m. by 1 hectopascal, the pressure at 3 p.m. will increase by, we know that the slope is over here, so therefore it will increase by 0.8894 hectopascals, as the response variable is also in hectopascals. 5b, use the equation of the least squares line to predict the atmospheric pressure at 3 p.m. when the atmospheric pressure at 9 a.m. is 125 hectopascals. Round your answer to the nearest whole number. So basically we're just going to use the equation of the least squares line as it says in the question. So we know pressure at 3 p.m. is equal to 111.4 plus 0.8894 times the pressure at 9 a.m. And we know that in the question it says that the pressure at 9 a.m. is 125 hectopascals, so you just solve 125 into the equation. If you put that on your calculator, you'll get 1,023 hectopascals rounded to the nearest whole number, as it states in the question. 5c, is the prediction made in part B an example of extrapolation or interpolation? So in 5b, we were predicting the pressure at 3 p.m. from the atmospheric pressure at 9 a.m., which was 1,025 hectopascals. So to determine if 1,025 hectopascals is interpolation or extrapolation, we need to see if 1,025 hectopascals lies within this data set. So 1,025 hectopascals is there, so therefore interpolation is being used because 1,025 is within the original data set. So therefore interpolation has been used. 5d, determine the residual when the atmospheric pressure at 9 a.m. is 1,013 hectopascals. Round your answer to the nearest whole number. So you should know that the formula for the residual is the actual value minus the predicted value. So first let's find the predicted value. So the predicted value would be found using the least squares regression line. So we know that the equation is over here. So use that equation. 111.4 plus 0.8894 times the pressure at 9 a.m. In the question it says we would determine the residual when the atmospheric pressure at 9 a.m. is 1,013 hectopascals. So you sub 1,013 in the equation. If you do that, your predicted value should be 1,012.3622 to 4 decimal places. And to determine the actual value, we need to look at the scatter plot. So we are determine the residual when the atmospheric pressure at 9 a.m. is 1013 hectopascals. So you go up here, pressure at 9 a.m. in hectopascals. So you look for 1013 on the x-axis. 1013 is over here. 1011, 1012, 1013. So that's where 1013 is. So you go up and you look where the dot is. And the dot for this is representing the point 1013 and 1015. So actual value is the y value for this point, which is 1015. So we know the actual equals 1015. So basically all you have to do now is just sub these values into the residual formula, and you'll find the residual. So the actual is 1015 minus the predicted, which is 1012.3622. If you do that, you'll get 2.64, and the question says round to the nearest whole number, so therefore 3 hectopascals round to the nearest whole number. 5 EI. The mean and standard deviation of the pressure at 9 a.m. and pressure at 3 p.m. for these 23 days are shown in Table 4 below. Use the equation of the least squares line and the information in Table 4 to show that the correlation coefficient for this data, round to 3 decimal places, is R equals 0.966. So to do this, we need to actually know the rule for the value of the slope. And here it is over here. B equals the value of the correlation coefficient times the standard deviation of y on the standard deviation of x. So we know from the slope that the pressure at 9 a.m. is the x value, or the explanatory variable, and the pressure at 3 p.m. is the response variable. So basically we know that the value of the slope, if you look at the least squares regression line, slope is 0.8894. So we know B equals 0.8894. So sub the standard deviation of x and y into the formula and the slope to find the correlation coefficient, which is the value of R. So 0.8894 equals R, correlation coefficient, times the standard deviation of y. Standard deviation of y is over here, 4.1884, on the standard deviation of x, which is 4.5477. So now we need to solve for the value of R, since it is a show that question. So since it's a show that question, we must show our steps to find the value of R. So R times 4.1884 equals 0.8894 times 4.5477, and then R would equal 0.8894 times 4.5477 on 4.1884. So I'm just solving using algebra. If you put that on your calculator, you'll get the correlation coefficient is 0.966 to 3 decimal places. 5 EII. What percentage of the variation in pressure at 3 p.m. is explained by the variation in pressure at 9 a.m.? Round your answer to 1 decimal place. So basically, this question is asking us to find what is the coefficient of determination as a percentage. So to find the coefficient of determination, that's basically the R squared value. So all we need to do is square the value of R, which we have given to us in the previous question. So if you put that on your calculator, you'll get 0.933, 0.966 to the power squared. You get 0.933. So as a percentage, you have to time this by 100, which would give you 93.3% correct to 1 decimal place. 5F, the residual plot associated with the least squares line is shown below. The residual plot above can be used to test one of the assumptions about the nature of the association between atmospheric pressure at 3 p.m. and the atmospheric pressure at 9 a.m. What is this assumption? So you should know that residual plots are used to determine whether the association between two variables is linear or nonlinear. So basically, it's just a linear assumption. We are trying to determine whether there is a linear assumption between two variables. So 5 II, the residual plot above does not support this assumption. Explain why. So you should know that if there's a pattern in the residual plot, then that's indicating a nonlinear relationship. If there is a random pattern of dots in the residual plot, then that means there is a linear association between the two variables. However, in this case, we can see that the residual plot has a sort of curve pattern like that. There is some sort of pattern to the points. So we're gonna say, since there is a clear pattern in the residual plot, this indicates a nonlinear association between the two variables, which are atmospheric. So nonlinear association between atmospheric pressure at 3 p.m. and the atmospheric pressure at 9 a.m. Then you can have a concluding statement. Therefore, the residual plot does not support this assumption. It does not support a linear assumption. So that would be your response. Question 6. The total rainfall in millimeters for each of the 4 seasons in 2015 and 2016 is shown in Table 5 below. The seasonal index for winter is shown in Table 6 below. Use the values in Table 5 to find the seasonal indices for summer, autumn, and spring. Write your answers in Table 6 rounded to 2 decimal places. So basically, to do this question, the first step is to find the seasonal average for 2015 and 2016, which I've already done. So the seasonal average for 2015 is 160, and the seasonal average for 2016 is 150. So now basically you calculate the seasonal indices for, so first step, we want to find the seasonal index for summer. So to do this, find the seasonal index for 2015. We know that the formula for the seasonal index is actual on seasonal average. So if we use this formula for 2015, the actual value for summer 2015 is 142, divided by the seasonal average for 2015 is 160. And then since we have another year as well, which is 2016, you add the seasonal index for 2016 summer, which is 135 divided by 150. And basically you're sort of finding like the average seasonal index of the 2 years. So you divide it by 2. If you put that on your calculator, you'll get 0.89 rounded to 2 decimal places. So we'll do the same thing for autumn. Seasonal index for 2015 for autumn is 156, the actual, divided by the seasonal average, which is 160, plus the seasonal index for autumn 2016, which is the actual value, 153, divided by the average for autumn in 2016, which is 150, and you do that divided by 2. If you put that on your calculator, you'll get 1.00 to 2 decimal places. And winter has been done for us. So for spring, we'll do the same thing. Actual value, 120, divided by the seasonal average, which is 160 for 2015, plus the seasonal index for 2016 in spring is 96 divided by 150. Divide that by 2, put that in your calculator, and you get 0.70 to 2 decimal places. Question 6b, the total rainfall for each of the 4 seasons in 2017 is shown in the table 7 below. Use the appropriate seasonal index from table 6 to deseasonalize the total rainfall for winter 2017. Round your answer to the nearest whole number. So we know that the formula for for the deseasonalized rainfall would be the actual value in 2017 minus the seasonal index. So we want to find the deseasonalized value for the total rainfall for winter in 2017. So the actual value for the total rainfall for winter is 262 millimeters. So write 262 divided by the seasonal index for winter. So from table 6 we know that the seasonal index for winter is 1.41. So write 1.41. Put that on your calculator and you get 185.82 to 2 decimal places. But the question wants us to round the value to the nearest whole number. So therefore 186 is the millimeters is the deseasonalized rainfall for winter 2017.